Let P and Q be two propositions. P, it is raining, and Q, John is sick. Write each of the statements below in terms of P and Q. It is not raining, so that's not P. Or John is sick, so R, and John is sick would be Q. If it is raining, then John is not sick. So P, it is raining, and that implies, this is a conditional statement, John is not sick, so that's not Q. So P implies not Q. An operation, and we can see the operation there, asterisk, is defined on the set 1, 2, 3, and 4, as shown in the following table. Prove that the operation is commutative. Now, if commutative, what is that if? If the operation is commutative, then A, B is equal to B dash A. Alright? So notice the diagonal here. Yes, so notice 1 asterisk, say for example 2 is equal to what? 4 is the same as 2 asterisk 1 there, same 4. Alright, so notice there's symmetry. So notice there is symmetry about the diagonal, or so the main diagonal, which would be, this would be the main diagonal here. And notice there's symmetry. Alright, 4, 4, and so on, 1, 1, 2, 2, and so on. Alright, and notice for all elements on the set, there's commutativity in terms of, notice 3 asterisk 2, which is this value here, is same as 2 asterisk 3. Same value 2. And you can try for all the members of the set. You will realize that you have commutativity. Alright? Part 2. Show that the identity element of asterisk is 3. Now the thing about identity elements, notice for example in number theory the identity element is 1, which means that any value times 1 you get back the same value, right? For example 4 times 1 is 4 and so on. 5 times 1 is 5 and so on. So notice in this table here 1 asterisk 3, you get back 1, right? And it's the same case for all elements in this set. Notice the same for 2. You get back the value 2 asterisk 3 is 2, and so on. It's the same for all elements. 3 asterisk 3, you get back 3, and for 4, the same result. 4 asterisk 3, you end up with 3. So in other words, multiplying an element by 3 does not change the value. Let's write a statement here. So for any element A, which is a member of the set 1, 2, 3, 4, and A asterisk 3, you get back the same element A. Alright, hence 3 is the identity element of the operation. Next, the polynomial f of x equal ax cubed plus 9x squared minus 11x plus b has a factor of x minus 2 and the remainder of 12 when divided by x plus 2. Show that a is equal to 2 and b is equal to minus 30. So we are told the function has a factor of x minus 2, meaning when divided by x minus 2, there's no remainder. So f of 2 would give you a remainder of 0. Alright, so let's find f of 2. Remember what it means to be a factor, right? A factor means when divided by that value, there's no remainder, or the remainder is 0. So f of 2, we're replacing x with 2. So it's a times 2 cubed plus 9 times 2 squared minus 11 times 2 plus b. That should be equal to 0. Let's simplify. So 2 cubed, that's 8. So 8a. 2 squared, that's 4. 4 times 9, that's 36. 11 times 2, 22 plus b. We can group the constants, of course. So we have 8a plus b, and 36 minus 22, that's what? 14. So plus 14 is equal to 0. I'll just call this equation 1. We are also told that the polynomial, when divided by x plus 2, we get a remainder of 12. So this means that f of minus 2, I must put it down here, f of minus 2 is equal to 12. And now we can substitute minus 2 for x in the function. So we have a times minus 2 all cubed plus 9 times minus 2 squared minus 11 times minus 2 plus b, and this is equal to 12. So negative 2 to the power of 3, that's negative 8, so negative 8a. So the 36, 4 times 9. Negative times negative, that's positive 22 plus b equal to 12. And I'll simplify this. Let me just put it down here. So minus 8a, put it here. So minus 8a plus b, and then 36 plus 22, that's what? 58 is equal to 12. And I'll just label this as equation 2. So we have a pair of simultaneous equations here. So let's add both equations. Now, to solve simultaneously, of course, we can add, let me just add both equations. So I'm going to add both equations, right? Equation 1 and equation 2. So when we add both equations, notice 8a plus negative 8a, that's 0. b plus b, that's 2b. 14 plus 58, that's what? No, that's 72. And 0 plus 12, that's 12. So notice we can subtract 72 from both sides. So 2b is equal to 12 minus 72. So this becomes 2b is equal to, what's 12 minus 72? Negative 60. Divide both sides by 2. The value of b would be minus 30. Let's now find the value of a, and to find the value of a, we substitute the value of b into any one of the equations. Let me substitute it into equation 1. So I'm going to substitute b equal minus 30 into equation 1, which means that wherever I see a b in equation 1, I replace it with minus 30. So I'll have now 8a, replacing b with minus 30, I'll have minus 30 plus 14 is equal to 0. So 8a, negative 30 plus 14, that's what? Minus 16 equals 0. Add 16 to both sides, so 8a will be positive 16. Divide both sides by 8, a is equal to 2. So our solution, a is equal to 2 and b is equal to minus 30. Solution to the problem here, a is 2, b is negative 30. So that's proven. Hence we're asked to solve this polynomial here. So a is 2, b is negative 30, so we can rewrite this as 2x cubed, since a is 2, plus 9x squared, minus 11x, and b is minus 30. So minus 30 is equal to 0. Now remember, we are told that x minus 2 is a factor now. Alright, so we can use synthetic division to get the other factor. Alright, so using synthetic division, and of course you could also use long division, but let me use synthetic division, using x minus 2 as a factor. Recall that x minus 2 is a factor, right? So, of course, x minus 2, so I'll put 2 out here using synthetic division. So I'll put the coefficients of the polynomial, which would be 2, 9, minus 11, minus 30. Alright, so I bring down the first value 2, and I say 2 times 2, that gives me 4. So 4 plus 9, that's 13. I say 2 times 13, that's 26. Negative 11 plus 26, that's 15. And I say 2 times 15, that's 30. Negative 30 plus 30, that's 0. So this 0 represents the remainder, which is what we expect since x minus 2 is a factor. The other values would be the coefficients of the quadratic. So the other factor would be 2x squared, plus 13x plus 15. And we can equate this to 0. And we can solve this whether by the quadratic formula or factorization. I'm going to use factorization. Now to solve by factorization, we are going to rewrite the middle term, which is a 13x. Remember, recall AC. The value of AC is what? 2 times 15, which is 30. If I write down all the factors of 30, 6 times 5, 30 times 1, 2 times 15, 3 times 10. I select the pair that adds to give 13, which will be 3 and 10. So I'll rewrite the middle term as 2x squared plus 10x plus 3x. So I rewrite the 13x as 10x plus 3x. Why 10x plus 3x? 10 times 3 gives us the same as AC, which is 30. And then our factor by groups. So the first pair, the highest common factor there is 2x. And for factor 2x with x plus 5. The other pair, the common factor for 3x plus 15 is 3. And I will be left here with x plus 5. Alright. So the factors would be x plus 5 and 2x plus 3. And of course, to solve this equation, we equate both brackets to 0. So x plus 5 equal to 0. And 2x plus 3 is equal to 0. Therefore, x equal to minus 5. And solve this equation, 2x equal to minus 3. So x equal to minus 3 upon 2, or minus 1.5. And also the solution will be x equal to 2, since recall x minus 2 is a factor. So these will be the solutions for the cubic polynomial: minus 5, minus 3 over 2, and positive 2. Next question: use mathematical induction to prove that 8 plus 6n plus 24 plus 32 plus that plus 8n is equal to 4n into n plus 1. Now, of course, proof by mathematical induction, we follow 3 basic steps. So step 1 would be to show that the statement is true for n equal to 1. Notice when n equal to 1, 8 times 1 is equal to 4 times 1 into 1 plus 1. So 8 equal to 8. So left hand side equal to right hand side. Therefore, statement is true when n equal to 1. Step 2, assume the statement is true when n is equal to k. So we can replace all values with k. So it means that 8 plus 16 plus 24 plus 32 plus 8k is equal to 4 times k into k plus 1. And the third and final step is to show true. So the third step is to show true that when n is equal to k plus 1. So show true when n is equal to k plus 1. Alright? So when n is k plus 1, that's an additional term to the second step. So notice 8 plus 16 plus 24 plus 32 plus that plus 8k. Now the question is which term would follow 8k? Now notice the terms are increasing by 8. Remember the sequence 8, 16, 24. So the terms are increasing by 8. So the term that would follow 8k would be 8k plus 8. And I put a question mark here because we're asking a question: is this now equal to the right hand side? And on the right hand side, we're going to be replacing n with k plus 1. So 4 times n becomes 4 times k plus 1. And in the bracket, we have replacing n with k plus 1. So it's k plus 1 plus 1. And our task is to show that the left hand side is the same as the right hand side. Now let's do that. Now, left hand side. Now the left hand side, let me just rewrite the left hand side. If you notice on the left hand side, 8, summation from 8 to 8k. Notice the same as in step 2. The summation from 8 to 8k is equal to 4k into k plus 1. And of course, additionally, there is 8k plus 8. So we're asking, is all of this equal to the same as we have on the right hand side? Let's prove it. So notice, so we have 4k into k plus 1. We can factor 8. In this term we can factor 8. So factor 8, we have 8 into k plus 1. Notice k plus 1 is a common factor. So we can factor k plus 1. And then in the other bracket, factor k plus 1. In the first term we're left with 4k. And we'll be left with 8 here. Now, is this the same as the right hand side? Let's see. Notice we can, so k plus 1, for the 4k plus 8, we can factor 4. We will be left with k plus 2 if we factor 4. And this is the 4 we can put here, or we can put at the front. And of course, 2 is 1 plus 1, right? So I'll just rewrite the 4, put the 4 at the front. So this is k plus 1. And then, what we have here now? K plus 1 plus 1. Notice the same expression we have on the right hand side. So this is equal to the right hand side. So therefore, statement is true when n equal k plus 1, hence true for all natural numbers n, where n is a member of a set of natural numbers. Now question 2, we're going to be using two methods to prove that if a squared plus b squared equal to 14ab, then a logarithm, natural logarithm of a plus b upon 4 is equal to half ln a plus ln b. Now, recall that a plus b all square is equal to a square plus b square plus 2ab. This means that, can do some transposing here, a plus b all square, subtracting 2ab from both sides, so minus 2ab is equal to a square plus b square. Alright? Now above there we are told that a square plus b square is equal to 14ab, so we can replace it. So we can replace a square plus b square on the right hand side with 14ab, which means if I add 2ab to both sides, I'll end up with a plus b square equal 14ab plus 2ab. So a plus b square is equal to 16ab. And of course I can take log of both sides. So if I log both sides, let me just log both sides now. So ln a plus b all square is equal to ln 16ab. Now, this 2, the law of logarithm, this 2 power here we can move to the front, so it's 2 ln a plus b, and of course we can use another rule of logarithm to separate, so it is ln 16 plus ln a plus ln b. I can now subtract ln 16 from both sides, so I end up with ln a plus b minus ln 16 is equal to ln a plus ln b. And of course I can divide both sides by 2, or divide each term by 2, or multiply each term by a half. Alright, so let me divide by 2. So I divide by 2. and I divide the right hand side by 2. So I'll end up with 2 into this here. I'll end up with ln a, so I divide each term by 2, so ln a plus b. And then ln 16 over 2, that's half ln 16, right? Is equal to, and I can rewrite this as half into ln a plus ln b. And of course, ln a plus b, this is now minus ln 16 to the power of half, which is same as root 16. So half ln a plus ln b. And then now I'll end up with, on the left hand side, remember the square root of 16 is 4. So all of this will be 4, right? So 16 to the power half is 4. So rule of logarithm there. So ln, you can just combine the logs. So a plus b, so just subtract a plus b upon 4. And I'm using this rule. Ln a minus ln b is equal to ln a upon b. And that's the rule I use to combine these two expressions here, these two terms. And of course, the right hand side is half ln a, half ln a, plus ln b. And of course, this is what we're asked to prove in the first place. I'm just, alright. Quite easily done. So remind you of what the proof was. Ln a plus b upon 4 into half equal half into ln a plus b. Alright, let's do this proof using another method. Another method would be to begin with the equation ln a plus b upon 4 equal to half ln a plus ln b. Alright, so this, we could rewrite the right hand side, so ln a into ln a plus b upon 4. So what am I doing? So ln a plus b upon 4 is equal to, no, we can rewrite the right hand side. Now ln a plus ln b is ln ab. Alright, ln a plus ln b is actually ln ab, right? And of course, half. Now one thing we could do is multiply both sides by 2. So I'm going to times both sides by 2. So end up with 2 ln a plus b upon 4. And then 2 times half is 1, right? So I just have ln a plus b on the right hand side. And of course, law of logarithm. This 2 we can put here. So we can write this is ln a plus b upon 4 all raised to the power of 2 equal ln ab. So we have, and of course now we can just drop the logs. So we have a plus b square, a plus b upon 4, a plus b upon 4 all square is equal to ab. Now let us expand. So we expand, we'll end up with, so expand this, we end up with a square plus b square plus 2ab. And we square the denominator, of course, we get 16 is equal to ab. And of course we can times both sides by 16. we end up with a square plus b square plus 2ab is equal to 16ab. And of course we can subtract 2ab from both sides, so we'll end up with a square plus b square equals 16ab minus 2ab, which means that a square plus b square is equal to 14ab. And that's what, so hence proven quite easily. So either methods could be used to prove the expressions. Next problem here is a log equation. So maybe what we could do is to get rid of the negative power, we can times each term. We can times each term by 2 to the power of x, right? So 2 to the power of x times 2 to the power of negative x. You add the powers, right? It's in the same base, so it's 2 to the power of negative x plus x. So 2 to the power of 0. Plus 2 to the power of x times this term, with 3 times 2 to the x times itself. That's 2 to the x all square, right? Or 2 to the 2x if you prefer. And then 2 to the x times the right hand side. You end up with 4 times 2 to the power of x. Now, to make the calculations easy, we can let 2 to the x be equal to y. Let 2 to the x be equal to y. So hence we'll end up with, no, 2 to 0 of course is 1. So we're letting 2 to the x be equal to y. So this will be 3y squared equal to 4y. So we have a quadratic. Let's group everything on one side. So we have 3y squared minus 4y plus 1 is equal to 0. And of course we can factorize. Let us factorize. Alright, to factorize this, of course, is 3y. And 3y times y I give y squared, right? And the final term there is positive 1, which we get by multiplying. Alright, negative 1 times negative 1. So, you create both brackets to 0 and solve. You get y equal to 1 or y equal to a third. Now recall that 2 to the x was equal to y. So therefore, 2 to the x would be equal to y, which is 1, or 2 to the x is equal to 1/3. And of course we can log both sides. So we log both sides, so ln 2 to the power of x is equal to ln 1. And over here, so ln 2 to the power of x is equal to ln a third. Good. Now here, we can move the power here. So x ln 2 is equal to ln 1. Now the value of ln 1 is 0. So x is equal to 0. That's one solution. Over here, x ln 2 is equal to ln 1/3. Divide both sides by log 2. So x is equal to ln 1/3 divided by ln 2. So our two solutions, x equals 0 or x equal ln 1/3 divided by ln 2. Number 2, part B. The following diagram shows a graph of the function f of x is equal to 3x minus 4 upon x plus 4. On the diagram, insert the asymptotes for the function. Now the asymptotes we'll get by equating denominator to 0. So asymptotes x plus 4 is equal to 0, which means x equal negative 4 is an asymptote. Alright? And the other asymptote is the value of the function as x approaches infinity. And of course, we can just use the coefficients of the x. For the numerator, it's 3, and for the denominator, the coefficient here is 1. So the asymptote, the horizontal asymptote is y equal 3. The vertical asymptote is x equal negative 4. So we can insert those on the diagram. Just to do that, so x equal minus 4 and y equal to positive 3, which would be positive 3 would be somewhere there. And of course, you should use a ruler, of course. Alright, notice our asymptote, notice the graph. Notice the curve does not touch the asymptotes. Alright? Get closer but doesn't touch it. So this is a straight line, should be y equal positive 3, and the other asymptote x equal negative 4. So this would look something like here. So of course a straight line. That should be a straight line, right? So of course you'll draw that much better. Alright, so it should be a straight line, x equal negative 4. So draw the line negative 4 through the x-axis straight down. Alright, and notice that the curve should not touch either of the asymptotes. Alright, next, sketch the graph of the inverse of f showing the asymptotes of f inverse. Now, how do we get the inverse of the function? You get the inverse of any function by reflecting that function in the line y equal to x. And what happens when you reflect a line in the line y equal to x? When we first sketch a line y equal to x, it will look like this, of course. We'll use a ruler, of course. And of course, this line will pass through. Alright. So that's the line y equal to x. And if we should reflect a point, reflect any point in the line y equal to x, of course, those coordinates will switch places. So here's a graph. So let me first focus on the piece over here. Let me just change it color. Let me use green. So let me focus on the piece over here. Let me just reflect this piece in the line y equal to x. So notice we have a point here. We have a point here. Negative 5, 15. Negative 5, 15 will now become 15, negative 5, which will be somewhere about here. Let me just select another point. Now, one strategy you could use is to find the actual inverse of the function. So we can let y be equal to 3x minus 4 upon x plus 4. Interchange x and y, we get x equal to 3y minus 4 upon y plus 4. And of course we solve for y. So we end up with xy plus 4x is equal to 3y minus 4. And we group the y's, so we group the x's over here. We have 4x plus 4. And if we group the y terms, it would be 3y minus xy. So we have 4x plus 4 upon, if I factored y, I would have 3 minus x. Divide both sides by 3 minus x. I'll get 4x plus 4 upon 3 minus x equal to y. And this y, of course, will be the inverse of the function. So, to get the asymptotes, of course, would be the value. The horizontal is the value that makes the denominator 0, which would be positive 3, right? Let's draw the positive 3. X equal positive 3, right? Good, which would be somewhere about there. And the vertical asymptote would be the value. The coefficients would be 4 for the x, and the numerator is 4. And in the denominator, is minus 1. say y equal to 4 upon minus 1, which is minus 4, which would be about here. Alright, and remember the horizontal, well, sorry, this is the horizontal, right? The vertical would be x equal to 3. So of course, the graph, and put it in green. So the graph would be something like that. Alright. Inverse, that is. And then for the other piece, which is this piece, and this other side here, of course, will end up on the other side of the other quadrant, which would be approximately here. Alright, so what I have in green, of course, it shouldn't touch it. What I have in green would represent the inverse. Of course, remember, this graph must not touch the asymptotes, okay? So it will look something like that. Given that alpha, beta, and gamma are the roots of the equation x cubed plus 3x plus 2 equals 0, form an equation whose roots are beta, gamma, alpha, beta. Now, recall that the sum of, for this equation here, x cubed plus 3x plus 2, recall the sum of the roots of any cubic polynomial is negative b over a. And notice b is a coefficient. B is a coefficient of the x squared, and there's no x squared term there, so of course 0. The sum of the products, which is alpha beta plus beta gamma plus alpha gamma, is equal to, so the product, the sum of the product would have c over a. Now c is the coefficient of the x, which is positive 3, right? A is 1, so 3 over 1, which is 3. And then the product of the root, that's alpha beta times gamma, is negative d over a. Now d is a constant, which is 2, so negative d would be minus 2. Alright, so now we're asked to form an equation whose roots are beta gamma, alpha gamma, and alpha beta. Alright, so cubic equation, let's put it up here. So cubic equation whose roots are beta gamma, alpha gamma, and alpha beta is x cubed minus x squared times the sum. So the sum is beta gamma plus alpha gamma plus alpha beta plus the sum of the products. So we're going to take the product. So we're going to start the product now. So take the product of 2, which would be beta gamma times alpha gamma, which would beta gamma square times alpha, plus, we're going to take the product of these two now, alpha gamma times alpha beta, so that's alpha square beta gamma, plus, and we can take the product of the last two, so it's beta gamma times alpha beta, which would be beta square gamma alpha. And that's the coefficient of the x. And then the constant now would be the product. So the product of all these roots will be beta gamma times alpha beta. So basically beta gamma alpha all square. Should we take the product of all the roots? Now let's work out the value of all the coefficients. Now beta gamma plus alpha beta, we have the value already. That value is equal to positive 3, right? Now we calculate that value already. Now beta alpha gamma all square, beta gamma times alpha all square is equal to this minus 2 all square, which is equal to 4. And let's do the coefficient of the x, which would be, let's rewrite it, which would be beta gamma square alpha plus alpha square beta gamma plus beta square gamma alpha. What is this equal to? Now notice for this expression, beta gamma alpha is a common factor. So if I factor out beta gamma alpha, I'll be left with gamma for the first term. For the second term, I'll be left with alpha. And for the last term, I'll be left with beta. And of course, so outside we have the product, and inside we have the sum of the original cubic equation. Now the product was what? Minus 2. And the sum was 0. So all of this is equal to 0. So therefore the cubic equation, let's put it here. So therefore the solution is the cubic equation x cubed. Let me just remind you what the equation was. X cubed minus, and this the product, the sum of the products, which will be minus, so the minus 3x squared and the second term, the second to last term will be 0, of course, and then the constant, that's minus 4. This value minus the square of the product here, which would be 4. So the solution will be x cubed minus 3x squared minus 4 equal to 0. Question 3, prove the identity tan A plus B equal to tan A plus tan B upon 1 minus tan A tan B. I'm going to begin from the left hand side. Alright, so this is proof. No, so we'll begin from the right hand side. So the right hand side, I'm going to rewrite tan A. So the numerator, I'm going to rewrite tan A as sin A upon cos A. and tan B as sin B upon cos B, divided by, and the denominator is 1 minus tan A, that's sin A, upon cos A, times sin B upon cos B. Now let's see how best we can simplify this now. So the numerator, which is the first bracket here, we can common denominator would be cos A times cos B, and sin A cos B plus sin B cos A, divided by, over here now, the common denominator would be cos A cos B, and so 1, we of course will rewrite 1 as cos A cos B, right? So divide by, right? Let's separate. And minus sin A sin B. Now of course, this would be sin A cos B plus sin B cos A upon cos A cos B times, and we can reciprocate over here, so we end up with cos A cos B upon cos A cos B minus sin A sin B. So notice cos A cos B into itself, we end up with 1. So at the top here, recognize that this is actually sin A plus B, and in the denominator here, this is actually cos A plus B, and of course this is equal to tan A plus B, which is what the left hand side is equal to. Therefore, quite easily proven. So given that sin A is 3 over 5, let me just draw a right angle triangle here. So sin A, remember sin is opposite upon hypotenuse. So the opposite would be to A would be 3 and the hypotenuse would be 5, which means the adjacent would be 4. So sin A is 3 upon 5. And cos B, so A is acute and B is an obtuse angle. So it means that cos A would be adjacent over hypotenuse, which is 4 over 5. And let's do angle B. So we're told that angle B is a obtuse angle, but let me just make it acute for now. Now cos is adjacent over hypotenuse, so 1 upon 2, which means that the opposite to B would be root 3. So remember, cos B is an obtuse angle, -1/2. But for the obtuse angle, remember that the sign is still positive, which means that sin B is opposite over hypotenuse, which would be root 3 upon 2. Alright? Now we're asked to find, express, and of course, tan A is opposite over adjacent, which is 3 over 4. And tan B, of course, if its angle is obtuse, tan B would be a negative angle. Tan B is what? Opposite over adjacent, which would be negative root 3 upon 1. So we're asked to find tan A plus B. So tan A plus B, remember that tan A plus B is tan A plus B is tan A plus tan B upon 1 minus tan A times tan B. Now let's plug in the values now. So tan A is 3/4, so it's 3/4, plus tan B is negative root 3, so 3/4 plus minus root 3, so it's 3/4 minus root 3. Divide by 1 minus tan A tan B, so it's 1 minus 3/4 times minus root 3. Let's see if we can simplify and rewrite in the form A plus B root 3. So 3/4 minus root 3. So I need a common denominator, put the root 3/1. So a common denominator would be what? 4. And this would be 3 minus 4 root 3. Divide by 1 here. So 1 upon 1. So of course the common denominator will be 4. So the 4 and negative times negative is plus root 3. So this becomes 3 upon 4 root 3 upon 4 times 4 upon 4 plus root 3. 4 into itself, that's 1. So we end up with just 3 minus 4 root 3 upon 4 plus root 3. But of course, to rationalize, we can multiply by the conjugate of the denominator. The conjugate of 4 plus root 3 is 4 minus root 3. So we multiply numerator and denominator by the same value to make the fraction equivalent. Right, so we end up with, let's expand. So we end up with the denominator will be just 1. Alright, 4 minus 3, which is just positive 1. The numerator, let's expand now. So 3 times 4, that's 12. 3 times minus root 3, that's minus 3 root 3. And minus 4 root 3 times 4, that's minus 16 root 3. And then what we end up with now, the final term, negative 4 root 3 times positive 4 root 3. So it'll be 4 times 3, which is positive 12. So the solution is 12 and 12, that's what, 24 minus 19 root 3 upon 1, which is just 24 minus 19 root 3. Okay, so error was made here. This should be 3 root 3. So it's 4 3 root 3. So now I'm doing the expansion. So 4 plus root 3. So it's 4 plus 3 root 3. And the conjugate is 4 minus 3 root 3. So it will be 4 minus 3 root 3. So let me just redo the expansion. So expanding, denominator will be 16 minus 27. And the numerator is 3 times 4, that's 12. 3 times minus 3 root 3, that's minus 9 root 3. Minus 16 root 3. And then minus 4 times minus 3, that's 12. Times 3, that's positive 36. So the solution ends up becoming, well, negative 11 in the denominator, and numerator 12 and 36, that's 48. And minus 9 minus 16, that's what? Minus 25 times root 3. So this will be your solution. 48 minus 25 root 3 upon negative 11. Next, we have an equation to solve here. But I guess we can rewrite the sine square. We can rewrite sine square. Sine square as 1 minus cos square theta. And then we have minus 2 cos square theta. Plus 3 cos theta. Plus 5 is equal to 0. So we have minus. So we have 1 minus, and this is 3 cos square. So 1 minus 3 cos square theta. Minus and minus 2. Plus 3 cos theta. Plus 5 is equal to 0. I'll group everything on the right hand side. So I have 3 cos square theta minus 3 cos theta. And then 6, that's minus 6. Alright, divide each term by 3. I end up with cos square theta minus cos theta minus 2. And if we factorize, so cos theta minus 2 plus 1. Equate both brackets to 0 and solve. So cos theta plus 1 equals 0, which means cos theta is equal to minus 1, or cos theta is equal to 2, which is impossible. So we're just working with cos theta is equal to negative 1. If cos theta is equal to negative 1, it means therefore that theta is equal to the cos of which angle given negative 1 now. That's 180 degrees, or pi radians. Or on the other angle, add 2 pi, that will be 3 pi. So 3 pi radians. Or in degrees, that's 3 times 180. Right, so that's our solution. So next, we're asked to express 6 cos theta plus 8 sin theta in the form r sin theta plus alpha. Express it in, alright, so 6 cos theta plus 8 sin theta, where alpha is between 0 and 90 degrees. Now if we expand, we have r, and then this is what? Sin theta cos alpha plus sin alpha cos theta is equal to, well, 6 cos theta, right? Plus 8 sin theta. So if we can equate coefficients. Let's equate coefficients. Equate coefficients for, if we equate coefficient for on the right hand side for sin theta, and for sin theta on the right hand side, that's r cos alpha. On the left hand side is r cos alpha, and over here sin theta, the coefficient here is what, 8. And over here, the coefficient for cos theta over here is what, 6. And the coefficient here for cos theta here is r sin alpha. So if we divide both equations, what we get is just tan alpha, r sin alpha over cos alpha. R cancel r's, r sin over cos, that's the tan alpha, is 6 over 8, which is 3/4, right? Now if tan alpha is 3/4, let us draw a right angle triangle there. Call this alpha. Tan is opposite over adjacent, so this will be 5. So it means that sin alpha, so from here, r is 6 divided by sine alpha, which is 6 divided by, now sine alpha, that's opposite over hypotenuse, so 3 over 5, so 6 divided by 3 over 5, which is 6 times 5 over 3, which is 15. So r would be equal to 15, and from here tan alpha is 3/4, alpha would be equal to 36.87 if you're using a calculator. Alright, so we're also express this function in the form, so f theta in this form will be r, and what is r? 15 sine theta plus alpha, which is 36.87 degrees. Hence, or otherwise, find the general solution of f theta is equal to 2. So f theta, remember this, f theta was 15 sine theta plus 36.87 degrees. So we can divide both sides by 15, which means that sine theta plus 36.87 is equal to 2 upon 15, and of course theta plus 36.87 degrees is of course sine inverse 3 upon 15, which is equal to, alright, and now we can subtract 36.87 from both sides, so theta would be 11.54 minus 36.87, that's negative 25.33, and of course we want general solutions, so 360 degrees times n, or 168.46 minus 36.87, that's 131.59 plus 360 degrees n. So that's our general solution.